So two blocks of mass M1 and M2 are connected by a string over a pulley of mass MP and radius r, as shown in this figure. And in a previous question, you were asked to set up three equations and three unknowns that could be used to solve for the acceleration. But now we're going to solve it a different way using conservation of energy. So we're saying that block 1 is initially on the ground, and block 2 is a height h above the ground. So in part A, we want to derive an expression for the speed at which block 2 strikes the ground in terms of its initial height, the acceleration, which we're just going to call a, and any physical constants. So this is just going to be basic kinematics because we know the initial velocity is 0 as it was released from rest. The acceleration, we're just calling a. The delta y, the distance it falls, is h, and we want to find the final speed at which it hits the ground. So v is equal to question mark, which means that using the last kinematics equation, v squared equals vo squared plus 2a delta y, with vo going to 0, plugging in everything you need, you'll just get v is equal to the square root of 2ah. That's all you gotta do for part A. For part B, this is where we're going to use conservation of energy to derive a different expression for the speed at which block 2 strikes the ground, but this time it's going to be in terms of all the masses as well as that starting height. And there's a hint down the bottom of the page which tells you that when you set up conservation of energy, K initial plus U initial equals K final plus U final. Initially, the system is at rest, so K initial is equal to 0. U initial, one of the blocks, which is block 2, has gravitational energy. The K final, all three objects are moving. Both blocks are moving with translational kinetic energy, and the pulley is rotating with rotational kinetic energy. And the U final, block 1 has now gone up to a height h since block 2 went down by a height h. So none of the other terms in here are equal to 0. So plugging in the formulas, we have for the initial gravitational energy, remember it was block 2 that started out at height h, so it's m2 g h, and that's equal to the final kinetic energy, so both blocks are moving, so it's going to be 1/2 m1 v squared plus 1/2 m2 v squared plus the rotating pulley 1/2 I omega squared plus, now keep in mind all of this stuff was just that final kinetic energy. All three objects are moving, and then that final gravitational energy would be from M1, since M2 went down to the ground and M1 rose up off the ground. So M1 G H. Now, almost every term has an M in it, except for this one. So we're going to replace the I with the inertia of the pulley, and a pulley is shaped like a disc or cylinder, which if you look up the formula for that is 1/2 mr squared, so in this case 1/2 mp r squared. But now, do the m's actually cancel out of this equation? The answer is no, because there are different m's throughout, so we cannot actually cancel out the m's even though every term has an m in it. So we just need to find a way to start grouping some things together to solve for the v. And what we can do is, if you look at this formula that we just wrote for I, if I plug this formula in right there, you have an r squared and an omega squared both in that formula, which will be multiplied, and we know that since v is equal to r times omega, if you square both sides, r squared times omega squared will equal to v squared. So let's rewrite this whole thing now with everything in place. We have m2gh is equal to 1/2 m1v squared plus 1/2 m2v squared plus, now in this one we want to multiply this 1/2 right here by this 1/2 to give you 1/4 times mp v squared plus m1gh. We have 3 terms, all which have a v in them. So let's bring this term over to that side, factor out the v squared from all of this stuff, and you can also multiply everything by 2. That'll at least get rid of some of these fractions in here. And when you solve for v, what you'll end up with is v is equal to the square root of, and there's going to be a 2 in there, there's going to be a whole bunch of other stuff, and there's going to be an h in there as well. And the reason it's important for me to have the 2 and the h listed in addition to that whole bunch of other stuff is because of part C. When you equate the 2 expressions you got, this one from part A and this one from part B, both expressions have a square root, which you can cancel out. Both expressions have this 2, which cancels out, and both expressions have that h, which cancels out. But basically, everything else that was left inside there is going to be equal to that acceleration. So that's what you're trying to get to for part C.